So an example of a physical change would be like boiling or melting, or something of that sort. Um, and so if we look at the boiling process, we have water. Water has an oxygen in the center of it and then two hydrogens attached to it. So this would be a molecule of water here. And these four dots here represent electrons, which we'll talk about later. But if we have water boiling, the waters are kind of stuck together here in the liquid phase. And there are attractions between the water molecules like this. And so they're kind of stuck together. But if we boil it, what we do is we increase the temperature, and that will increase the kinetic energy. Eventually we'll hit a kinetic energy which is enough to separate these. In other words, they're kind of stuck together like this. They aren't like permanently stuck together. I mean, they can still break free and move around. So in liquid phase, they have what we call translational motion. But it's tough getting around because it's quite crowded. And, if we increase the kinetic energy, then they can really break free from each other. And so in the gaseous phase, there's going to be separation by empty space here. This empty space, there's no molecules, no particles in there. The empty space could still contain things like fields, like electric fields and magnetic fields, or these quantum fields. And so, it just doesn't contain atoms or molecules. And we call that a vacuum. There are different kinds of vacuums out there. But for us, this is the way we think about it. So the chemical identity doesn't change. So for example, we have water here, and we end up with water over here in the gas phase. So just right. LIQ just stands for liquid. In the gas phase, it's still water. And it's still going to have the properties that you expect for water. Now, what are the properties we expect for water? Water should have a boiling point of 100 degrees C. And so once we hit 100 degrees C, this is called its normal boiling point. Its boiling point can change, though, But even though its boiling point can change, it changes in a predictable manner. And so, for example, at sea level, we expect the boiling point of water to be 100 degrees C, but at higher elevations, do you know what happens to the boiling point of water at higher elevations? It doesn't increase, it decreases, just the opposite. And so, for example, if you were to boil water at an elevation, let's say a mile high like Denver, it boils at a little bit lower temperature. But that's one of the properties of water. It's a fixed thing. So it's something we can predict what the boiling point is at any elevation. And so, yes, the water does have fixed properties. Its boiling point is 100 degrees C under normal conditions being what we call sea level, but as we go up in elevation, the boiling point actually decreases. And if we use a pressure cooker, one of the advantages of the pressure cooker is that, what happens as the pressure goes up? Because at high elevation, did you know atmospheric pressure decreases? And so the air is thinner at higher elevations. But what happens if the air is thicker? If the air is thicker, do you know what happens to the boiling point? It increases. So pressure cookers have that advantage. And so at higher temperatures, things cook faster. There's an old rule of thumb. For every 10 degrees C temperature increase, cooking time is reduced by half, And so let's say if you're trying to cook something at 110 degrees C versus 100 degrees C, it should cook twice as fast. This is just rough estimate, but it's a reasonable estimate. So let's say you're trying to cook something at 90 degrees Celsius rather than 100 degrees Celsius. Well, what should happen to the cooking time there? It doubles. And so there's high elevation cooking instructions usually involve longer cooking times. If you're trying to boil pasta at 90 degrees C, it's going to take a lot longer than boiling pasta at 100 degrees C. So you might want to use a pressure cooker in that sense. But the boiling point doesn't drop that low in Denver, so the cooking times aren't doubled in Denver. But nonetheless, it's still water. Water has those characteristics. And when we say, with physical properties like this, the chemical identity doesn't change. That is, it's water molecules. Whereas in chemical change, chemical change is known as a chemical reaction. So when we have a chemical reaction, then the atoms are rearranged. So do you recognize this one? What is this called? Everybody should memorize this one. It's tetrahedral is the shape or the structure. It's like a ball. It's balanced, well balanced. Each of these legs are even. And so this is like one of these, if you rolled it, it would roll kind of like a ball. It's even though it looks kind of like a tripod. It doesn't really have a base, but
is that methane?
This is methane. Methane has the formula CH4, but when you look at the formula, it doesn't tell you what the structure is necessarily. So we have to figure out what the structure is, but this is methane. Methane is one of those ones people just memorize. So methane. Do you know what this is? This is called O2. Each of these is an O2 molecule. So we have actually two O2 molecules. O2 molecule up here and an O2 molecule here. One of the characteristics of O2, it has two lines here representing what we call a double bond. These are single bonds over here. This is a double bond. And so we have one methane molecule and two O2s. We represent that in the chemical equation like this. So CH4 plus two O2s. We can get even more descriptive by talking about the states. Do you know what the 4 states of matter are?
Liquid, solid, gas.
Yeah, good. Liquid, solid, gas. Usually people say solid because solids is the lowest energy. Then you heat the solid up and eventually it melts to a liquid. And then you heat the liquid up and eventually it'll vaporize to a gas. And then you continue heating the gas up. As you heat up the gas, what happens to the kinetic energy? It increases, and pretty soon the collision gets so violent, it tears things apart. And so in a flame, things are being torn apart. We get a plasma. The plasma is high energy gas. So oftentimes we'll write the state as like this. G stands for gas. S stands for solid. L stands for liquid. So these are gases here. And then what happens is the atoms get rearranged. Do you know what forms when you burn methane?
Carbon dioxide?
Yeah, it forms carbon dioxide. A lot of people are worried about carbon dioxide. So this is why some people are trying to ban all gas appliances. Methane burns very cleanly, but unfortunately it forms carbon dioxide. However, it could potentially form what? The black stuff, which glows yellow at high temperature. What's that? Not lava. Lava is actually molten rock, usually like
obsidian. Obsidian.
Obsidian is a mineral that's found in like certain rocks, like basalt.
Is it neon? Is it neon?
No, it's not neon.
Tar. Like the beach tar?
No, it's like the Bunsen burner. What do you want? You don't want a yellow flame in a Bunsen burner. Yellow flame's bad. We try to make a blue flame in a Bunsen burner because the yellow flame indicates what? Carbon monoxide and low oxygen. Low oxygen forms carbon monoxide and the black stuff, soot. What was the composition of soot? Soot's mostly like graphitic and amorphous carbon. It's just not completely oxidized or combusted. Um, so we have something called complete combustion and incomplete combustion. So if we don't have enough oxygen, then we are not going to form carbon dioxide. There's not enough oxygen, right? We'd form like carbon monoxide. We don't want to form carbon monoxide because carbon monoxide is worse. Why? This is carbon monoxide. Carbon monoxide is worse because it's very poisonous. Carbon monoxide attaches to your hemoglobin and prevents oxygen from attaching to your hemoglobin. So carbon monoxide preferentially bonds to hemoglobin.
Is it just CO?
Mm-hmm. Carbon monoxide, CO. Mono is one, and then oxide is oxygen. So one oxygen. Whereas carbon dioxide, di is two, and we have the two oxygens.
So when methane and the two and two combine together, you get carbon dioxide?
Hopefully we get carbon dioxide. If you got a blue flame, we're getting carbon dioxide. If you have a yellow flame, we're not quite there because we don't have enough oxygen. And so if we have enough oxygen, then we will have what we call complete combustion and form carbon dioxide. What's three?
Carbon trioxide?
Yeah, carbon trioxide. What about if you, if you open the holes in the burner even more, will you get carbon trioxide? Is carbon trioxide even better?
It's probably worse. Is it worse?
Well, actually, there's no such thing as carbon trioxide. We don't have to worry about carbon trioxide. And the reason is because this is maxed out. If you look at the periodic table, what do you think the most common charge on oxygen is based on its position in the periodic table?
4.
-2. Good. -2. -2 comes from each electron has a -1 charge and wants 2 more electrons because what number is it now? 8, and then it wants to go to either 10 or 2. If it goes to 10, it has to gain 2 electrons, giving a -2 charge. It'd be easier to go to 10 than it would be to go to 2. Do you see that? Because it's closer to 10 than 2. So if we pretend each oxygen is -2, we got 2 of them. That's -2, and this whole thing is 0 charge. That means carbon must be plus, well, just to add it up, -2 plus a -2 plus x gives 0. So carbon must be plus 4. If we went to carbon trioxide, it would be -2 plus -2 plus -2 plus what gives us 0? 6. Is 6 a viable option for carbon? What's the range for carbon?
Is it -2
Mm-hmm.
and like 3? No, 4.
No, it's not -2, but you're kind of on the right track. -2 is good for oxygen, but not necessarily the best for carbon.
-4 to +4?
Yes, -4 to +4. Exactly. Good. And so +6 is outside that range. The carbon trioxide is not. So we can use a little bit of theory. Yeah, we can form carbon monoxide, we can form carbon dioxide, but carbon trioxide wouldn't be expected to form. Normal carbon tetroxide typically needs 4 for carbon pentoxide, and needs 5. Those would all be ridiculous. So that's the two-pronged approach. The two-pronged approach is we're trying to use a little bit of theory and memorization. Memorization is, yeah, we form carbon monoxide, we form carbon dioxide. If we form soot, soot doesn't even have any oxygen on it. You know what soot is? Soot is just carbon. And there are different structures of carbon. It would be great if it formed diamonds, because then maybe it wouldn't be great. I don't know. then diamonds would be quite common, and then they wouldn't be so valuable. But soot is a solid, forms tiny particles of soot. Most of the soot is graphitic, or what we call amorphous. Amorphous, like graphite, has a very nice crystal structure, like ice, but amorphous doesn't have a well-ordered structure.
For soot, isn't it C like a subscript S?
No, soot is just SOOT. C with an S has different structures. We call the different structures of carbon allotropes. Carbon, we'll talk about that soon. But there are different structures we can have. Like pure carbon could be in the form of diamond. It could be in the form of graphite, or it could be in the form of soot, or charcoal, or coal. Coal is a mixture of different things. Graphite, amorphous, other forms of carbon. So it could be in the form of a mixture like that, or it could be in the form of these weird molecules called buckyballs and other things like graphene, etc. There are a whole bunch of different structures carbon can have. For CH4, there aren't a whole bunch of different structures. And for O2, there aren't. For CH4, this is the structure, this is the neutral structure. For O2, this is what we got. For CO2, this is what we got. Here, what we have here is, here, if I have one C, and I end up with two C's here, is that possible? No. So I made a mistake here. Let me correct this mistake here. I don't end up with two CO2s. I end up with one CO2 here. So if I start off with one carbon over here, I'm going to end up with one carbon, but now it's going to be bonded to oxygens rather than hydrogens. Where did the hydrogens go? The hydrogens went to form H2Os. H2Os can be written in different ways. Over here I have it bent like this. Over here it's straight, but these don't necessarily represent the structure. The more accurate representation is these upper drawings here rather than these lowers, but it doesn't really matter yet. And water is normally a liquid, so we'll just write H2O liquid. And so this is what we call the balanced chemical reaction. We can see how the atoms get rearranged. Now, what happens in that process? What happens in the process is in that flame plasma, all the atoms are being broken apart. That is, not the atoms themselves, but the bonds. The bonds holding these atoms together are being broken apart. And then the atoms get rearranged to form these. There's some conservation of energy, which is, this, let's say this is at 25 degrees C. How hot does the flame get? Not hot? Would you stick your finger in the flame? Probably not a good idea because it's extremely hot. It'll just cause severe burns. In fact, don't even stick your finger in the flame. If you grab something, a hot metal object, it'll cause severe burns. So you got to be careful. But what we're going to do is we're going to wait until it cools down. Is hot CO2, when it cools back down, let's say the flame is about 800 degrees C. So if the CO2 goes from 800 degrees C down to 25 degrees C, did its chemical identity change? Now we have, we went from hot CO2, which is about 800. But 800 is not enough to break the bonds. 800, what would you visualize looking at CO2 at 800 degrees C compared to looking at CO2 at 25 degrees C? How would you visualize the difference using a model in your head? How would a chemist visualize the difference? Pneumatic kinetic energy. So we would see this vibrating madly. And what else? Vibrating madly and breaking apart. It doesn't break apart. Yeah, 800 is not hot enough to break it apart. You'll be vibrating madly, and what else? Rotating madly, and
Transitioning.
close. Not, we don't call it transitioning. We call it,
Transitioning.
yeah, good, good. That's good. So we have rotational, vibrational, and so and translational. So it's just moving really fast. And so 800 degrees C is moving extremely fast. Even at 25 degrees C, CO2 is moving extremely fast. It's moving extremely fast, but you don't feel it because it's so small. Well, actually, you do feel it because if you were in a vacuum, you definitely notice the absence of things colliding with you. You know, we live under a blanket of air, and if that air were absent, if that is, if we got thrown into a vacuum, then that would cause some severe problems for us. So anyway, we'll just wait for it to cool down, and then we'll have at 800 degrees C, water will be steam. So we wait for the steam to cool down. At 100 degrees C, the steam condenses into liquid water, and then that liquid hot water cools back down to room temperature. So we wait for this to cool down to room temperature. But in the process, there's a chemical potential energy difference. Methane and O2 have a high potential. This is an explosive mixture. Is CO2 and water an explosive mixture? No, not really. This is stable. And so not only is mass and matter conserved, you know, conservation of mass, none of the atoms have disappeared, right? And no new atoms appeared, so the mass stays the same. So the number of grams on the reactant side is equal to the number of grams on the product side. But what was also realized was that energy is conserved. And so the total energy of the reactants is equal to the total energy of the products. Well, that's not the case because the potential energy has changed here. And so we went from a higher potential energy to a lower potential energy. So what we're going to get is we're going to get energy out. When energy gets spit out, do we call that exothermic or do we call that endothermic? Exothermic. And so this is a highly exothermic reaction. So energy is getting spit out here. And we have conservation of energy. So the total energy here is equal to total energy here. To make up for the difference here in the chemical potential energy, we have to have some energy released. What is the form of the energy? The form of the energy is you're going to get, you know, heat. And so that heat you can use to do different things. In other words, hot molecules.
So we're going from 800 degrees Celsius to 25 degrees Celsius? Or what's happening?
No, we're going from 25 degrees Celsius to 25 degrees Celsius. So we start off at room temperature, and does this room stay at 800 degrees C forever? No. What's going to happen to all the energy that's released from this? It's going to dissipate into the room, and eventually it's going to cool down to 25 degrees Celsius. It's not going to stay hot forever, right? Eventually it will cool down. So that's what I'm saying here. We wait for it to cool back down, and then we look at the total energy that's dissipated. If it's still hot, there's more energy being dissipated, right? And so we got to wait until it goes back down to room temperature so we can figure out how much total energy got released. Otherwise, it's not quite balanced. Does that make sense? Okay. So here we can see the states of matter here: solid, liquid, gas. The three common states of matter. Actually, plasmas are very common in the universe.
What's plasma again? How does that function?
You don't have to worry about it too much right now. This is the fourth state of matter, the plasma. Fires are plasma, but not just fire. The sun is a giant plasma ball. which is a fireball, I guess. But we have these are LED, but the old fluorescent lamps are plasma, neon lamps are plasmas, that kind of thing. So this is what we visualize. Of course, there's no motion here. What would you visualize in terms of kinetic energy?
Which one?
For all these? This is just a static picture.
The first one, the vibration.
Yeah, and would it be moving fast or slow, or what would it be moving?
Movement, please.
There would be movement, but would it be slow movement or fast? Slow. The middle one is, and the motion would be faster than a solid, right? And then the last one there is a gas. The movement would be very fast, but the plasma would be the fastest, and you're going to get violent collisions in a plasma. So that's kind of what we visualize. This is molecular dynamics. Here's a chemical change, just sugar, burnt sugar. So what they're doing is you could melt sugar, but you have to be very careful because some things don't melt. You heat them up and they start to decompose, And so it is possible to melt sugar and then re-solidify it and just freeze it, and it's still sugar. It still tastes like sugar. This is a partially oxidized sugar here. This is further oxidized. So what they're doing is they're just making charcoal. Charcoal. Charcoal is it's like eating soot, something like that. And so this is not going to taste very good. A lot of people like to taste caramelized sugar. It's a little different. But when we get to this, it's carbon and water. A lot of people, what they do is, if you have a bunch of, what do they call this here? Like your barbecue or your stove top has a bunch of carbon deposits on it.
That's what happens like with marshmallows when you burn them.
Yeah. Some people like it, like the taste of charcoal. It's like eating charcoal. If you burn it, that's very good. Is it pretty good? I suppose. Yeah. I don't. I like the golden brown caramelized marshmallows myself. But, So I'm very careful not to char it too much because I don't like the taste of soot. I don't like the taste of charcoal.
Could it be a physical change?
But there are. I'm sorry.
Could it be a physical change on a
Yeah. If I just melt this and re-solidify it, it would be a physical change. But these are examples of chemical change. Chemical identities completely change. One way you could get rid of these soot, you get this soot that's baked on. Like, I don't know if you have baking sheets. It's baked on there. So one of the ways that people get rid of the baked on carbon deposits is to cook it further. If they cook it further, you know what happens to the soot? It becomes further oxidized. Hopefully when you bake it off, it doesn't get oxidized to carbon monoxide. Hopefully it gets oxidized completely to what? Carbon dioxide, right? And so a lot of people just keep cooking it until the carbon gets converted into carbon dioxide. So a lot of people end up doing that to get rid of it, which is a lot easier than scrubbing it off. But cooking it off, you're using a lot of methane and generating a lot of CO2, and people are hypersensitive to CO2. This is why some people want to ban methane stoves. I think there was a ban in San Francisco and Los Angeles for new construction. For new construction, they're not allowing. New restaurant construction, they're not allowing gas appliances. Which for cooks is insane, yeah, because cooking on electric appliance, if you're a chef, is going to be not so easy. Yeah.
Can't you just tear off the black stuff?
Yeah, you could chip it off. Yeah. people use scrubbing pads and, wire brushes, stainless steel wire brushes, but it's a lot of labor. It takes a lot of muscle power because when it's baked on there.
If it's on a marshmallow, you tear it off.
Oh, marshmallow's easy, yeah. Marshmallow. But, you tear that off, it's not caramelized underneath. It's just kind of molten sugar underneath, melted sugar. All right. We're going to start with the classification of matter. We have pure substances and mixture. I already talked about this. Like sugar is a pure substance. Sugar, like table sugar, has what defines a pure substance? What defines a pure substance is a sample consisting of only one kind of matter. That one kind of matter is a fixed composition. If it has a fixed composition, then it has fixed properties. The properties that are characteristic of it. And so, table sugar, brown sugar is a mixture, but like white sugar has been processed, it should be pure. And so sugar and water, water is pure substance too. But sugar water is a mixture, and sugar water is going to have variable composition. You can make it less sweet or more sweet depending on how much sugar you put in that. And so that's the key characteristic of pure substances versus mixtures here. We'll talk more about that. So water, you heat water. This is called a heating curve. And so on the x-axis, we have energy. And as we add energy to it, it's going to increase the kinetic energy of this. So water starts off here, let's say at room temperature, and you heat it up, and eventually you hit 100 degrees C. When you hit 100 degrees C, then all the energy doesn't go into heating it up. All the energy doesn't go into its kinetic energy. You know what the energy goes into? The energy goes into its potential energy. In other words, what we're doing is we're breaking apart the water molecules. The water molecules are kind of stuck to one another. They're kind of sticky. And to break them apart will require to overcome that stickiness and vaporize that. And so that's where the energy is going here. So water boils at 100 degrees C, and it stays at 100 degrees C until all of it's boiled. However, sugar water, it boils at a little higher temperature depending on how concentrated it is. So sugar water could boil up here or it could boil lower, and the boiling point changes depending on what the concentration of the sugar is in the water. So people were saying, okay, there are some cooks that add salt to boiling pasta. And so one of the things that they were saying is maybe the salt increases the boiling point, because if you have a solution, the boiling point gets elevated like this. So maybe the salt increases it. But if you add it's true, salt will increase the boiling point, but you'd have to add fistfuls of salt in there to see a noticeable change in the boiling point. If you just add a pinch of salt in there, it's not going to do much. The boiling point, yeah, maybe a little bit higher, but nothing that's going to double this cooking time or increase it noticeably. So they're saying that the salt is not necessarily for the boiling point. The salt is for flavor, for taste. But conceptually, it's correct, because it does change the boiling point. The solution is not going to have the same boiling point, the mixture. So we can look at pure substances and mixtures at the particulate level. So this is pure bromine. Bromine, when we look at the periodic table, most of the elements in the periodic table are solids, liquids, or gases. What do you say? Most of the elements on the periodic table are solids. There's only, can you believe it? There's only one liquid on the periodic table at room temperature. Do you know what that one liquid is? Oh, okay, mercury. I'll make that two liquids. There are only two liquids. Mercury is one of them. And there's one more liquid.
Nitrogen?
Iron.
Nitrogen's a gas.
Magnesium?
Magnesium is solid. Iron's a solid. Bromine. Bromine's the other one. It's interesting. Do you see where bromine is? It's element number 35. Do you see that? What's above bromine? Chlorine. Do you know what chlorine is? Solid, liquid, or gas? Gas. It's a green gas. Chlorine's a green gas. What's below bromine? Iodine. Do you know what iodine is? Pure iodine? Solid, liquid, or gas? Solid iodine. It's a solid. Solid iodine is what we see at room temperature. So it's kind of interesting there. Bromine's a liquid, and bromine likes to form molecules. Molecules are two or more atoms bonded together. So bromine likes to form what are called diatomic molecules. Do you know what else likes to form diatomic molecules? Di means two atom molecules, diatomic. What else likes to form? Now there are 7 that you have to memorize. Excuse me, oxygen, correct. Oxygen likes to form. So if somebody says I'm breathing O2, excuse me, O2, they're talking about they're breathing oxygen. And that's oxygen in its normal form. Oxygen at room temperature likes to form diatomic molecules. However, in the flame, what happens to those diatomic molecules? They get broken apart. And so, excuse me, you have oxygen atoms. And those oxygen atoms would prefer to be bonded to another oxygen, but the kinetic energy in the flame keeps them separated. And then they collide. And in these collisions, they get excited. And they don't stay excited forever. And then as these atomic oxygen drop in energy, the energy is conserved, and they start spitting out, you know what color light? Blue light. So the blue flame comes from atomic oxygen.
What were the 7? I guess. Pure substances now.
Yeah, the 7 diatomic. So oxygen is another one, O2. Give me another one.
Bromine.
Bromine. So that's 2.
Hydrogen.
Hydrogen, H2. Yes, hydrogen likes to form diatomic molecules. H2. What else?
Chlorine. Chlorine.
No. You can kind of use the periodic table. Hydrogen, oxygen, bromine. What do you think about chlorine?
Sure.
Yes. What do you think about fluorine? Yes. Yeah, so iodine, bromine, chlorine, fluorine all like to form diatomic molecules. That's 4. Hydrogen's 5, oxygen's 6. We only have one more left. The one more left, we're breathing it right now. Nitrogen. Nitrogen. That's chapter 3. So this is pure bromine. This is pure water. This is bromine dissolved in water. So this is a mixture. And the mixture doesn't have fixed composition. That is, we can have higher concentrations, that is higher levels of bromine, or lower concentrations, lower levels. So this is, when we say a smaller amount of bromine, this is a larger amount of bromine. And it's going to be a darker color here, because bromine is the orange, red liquid. And so the mixtures will have variable composition, but the pure substances won't. The pure substances have fixed composition, therefore fixed properties. These are going to have different compositions and different properties. The properties are going to depend on the composition, how concentrated it is. When we have mixtures, they could appear homogeneous or heterogeneous. A homogeneous mixture would be like what we just looked at here. It's homogeneous to the eye, the unaided eye. It would be heterogeneous when we look here. because we got bromine and we got water, so that's heterogeneous. But when we look at this, it looks uniform. So homogeneous means it looks uniform with your unaided eye. And so this is homogeneous, this is homogeneous, this is homogeneous, this is homogeneous. Pure, what we call pure substances, in this case. In other words, substances are defined as elements like bromine or compounds like water. A compound is two or more elements bonded together. An element is just a single element. Even though this is diatomic molecules, it's still considered just bromine, pure bromine. Whereas mixtures are going to be multiple components here. It could be a mixture. This is a mixture of element and compounds here, or it could be a mixture of elements, or it could be a mixture of compounds, or whatever. But all four of these are homogeneous. So if we have something that's heterogeneous, then it has non-uniform appearance. And so typically, something that's heterogeneous has non-uniform composition with visibly different phases. But what would be, this is a trick question. What would be a heterogeneous that's pure? Do you know something that would be heterogeneous but pure? H2O. Ice water. Ice is pure water and water is pure water, right? So ice water is something that's heterogeneous, but its composition is uniform. But most of the time when we have heterogeneous, it's like sand and water. Is sand and water, look uniform? No, you got solid sand and water. It's non-uniform. Or something like oil and water. Oil and water, does it look uniform? No, you got a layer of oil usually on top of water. If something's homogeneous, then it could either be a pure or it could be a mixture. If it's a mixture, we call it a solution. This is out of order for me. When something's homogeneous, it's either a solution or which is a mixture, or a pure substance. And so solution is a homogeneous mixture. We could have heterogeneous mixtures. And phase, heterogeneous means there's two or more phases. So like in ice water, there's solid and liquid. In sand and water, we have solid and liquid. In oil and water, we have two liquids, but the two liquids don't mix. They're separate.
So if you have sugar water, it would be heterogeneous, but if it was oversaturated, it'd be homogeneous.
If you have sugar water, and it's all the sugars dissolve, so let's say you put some sugar cubes in water and they completely dissolve, that would be homogeneous. If you put too many sugar cubes in the water and not all of them dissolved, then it would be heterogeneous because you'd have some leftover sugar cubes. It turns out you can't dissolve an infinite amount of sugar in water. It's not possible. So let's say if somebody asks you, well, how many cubes of sugar do you want in your coffee? Do they still sell sugar cubes? Yeah. Or how many packs of sugar do you want in your coffee? Well, I'd like 20 packs. Do you think you could dissolve 20 packs of sugar in your coffee?
So like iced coffee and sugar, there's like sediments of sugar. It's not milk about coffee.
Oh, okay. Yeah. Like that. Heterogeneous and homogeneous. If you look at these just without this on the bottom, would you say homogeneous or heterogeneous? Look at what do we call these things? Yes. Not grad cylinders. You know what grad stands for? Grad stands for graduation. So there are graduations in the cylinder. And those graduations could be very precise or not very precise. The more markings, the higher the precision. So we have these three grad cylinders. You look at the liquid in there, do they appear homogeneous or heterogeneous? They look homogeneous. You know, I don't see any difference in phases. But it turns out that this is pure. This is pure water. You know what this is? Ethanol. Wow, it's good. Is it at the top? Oh, it doesn't. Oh, I thought you were looking at the molecules. Recognize the molecules. Clean it up good, bro. This is ethanol in water. Ethanol is kind of a weird one because, you know, you can't dissolve an infinite amount of sugar in water, but you can dissolve an infinite amount of ethanol in water. And ethanol and water mix in all proportions. So you could add so much ethanol in here that there's barely any water. But all those are homogeneous. However, this is pure, this is pure, this is a mixture. So a homogeneous mixture is called what? A solution. Now, solutions don't have to be liquid. Air, does air look homogeneous to you, the air in this room? Air is a homogeneous mixture, and we call it a solution as well. So we could have gaseous solutions, we could have liquid solutions, and we could have solid solutions. The most common solid solutions are alloys. Like, for example, if you look at 18 karat gold, does 18 karat gold look homogeneous or heterogeneous? It looks homogeneous, but did you know it's not pure? 18 karat gold is a mixture. It has some, what does 18 karat gold have? It has some silver in it. Whereas, the people should be honest about it. You know, if you're getting 18 karat gold, and you know, the mixture is going to have a composition. I think 18 karat gold is like 80% gold, right? You could be being scammed because it depends on how precise they measure it. You know, let's say they measure, okay, I'm going to have 80% gold. What's the symbol for gold? AU. And they go, okay, this I'm going to sell as 80% gold. But when you see 80% gold, you take, okay, that could be anywhere from plus or minus what? Plus or minus, I believe it'll be like plus or minus, because we represent things in certain ways. I'd say plus or minus 5. So anywhere from 84 to, let's say, 75%. We'll round to 80 here. This is the way we write numbers. And so let's say somebody's manufacturing 18 karat gold. It's supposed to be 80% real gold, but they're always giving you 75% and saying, no, that rounds to 80. Then you're being scammed, right? Or you might not be being scammed because maybe they're manufacturing 18 karat gold and they're putting 84%. And they say, okay, 84% rounds to 80, and then you're getting more gold. So you're coming out ahead. Right? And so, yeah, potentially you could be scammed, but you're not really being scammed because that's the precision of their measurement. The precision of the measurement, they go, that's 75%, that's close enough, right? Versus 80 point. If somebody writes 80 point, then we take the precision a little differently. And so if they put that decimal point there, then we treat that zero a little bit differently. And so we'd say 80 plus or minus 0.5, half of this digit here, percent. And so in this case, it would range from, let's say, about 80.4 to about 79.5%, right? Versus if they said, okay, I'm going to measure at 80.0%. If it's 80.0, then you're getting a narrower and narrower range, which is more accurate or more precise? More precise. And so in this case, we take half of this unit here, which would be 0.05. And so this would be anywhere from, let's say, 79.95, I'll just go from small to 80.04, because this would round down to 80. So I'll just cut it down to 4 rather than 5. And so here, you know, you're getting much closer to 80. Over here, who knows what you're getting, right? And so what is it? What is the definition of 18 karat gold? How precise is that definition? Is that definition of 18 karat gold extremely precise, so that something like if this were 75%, it wouldn't qualify? Or is the definition extremely precise, that is, that even, you know, if I don't know, actually. I don't know how precise that definition is or who, if there's some kind of standard.
Why do they call it carrot?
I don't, carrot is some, carrot is, they have lots of different units of measurement. I don't know the origin of it. There is I think a homework problem with carrots in there. And so we can relate carrots to a certain unit of mass. Well, I don't know how 18 karat came in there or 24. 24, do you know 24 karat is 100% gold? But how precise is 100%?
Same thing over here.
The same thing. Is it 100 or is it 100 point? Or is it 100.0 or is it 100.00? How pure does it have to be? And that usually costs a lot of money. And so some people when we buy chemicals, we always worry about this. Like if you buy helium to fill up a balloon versus you buy helium for certain purposes, we used to use this kind of helium. We used to use 99.9999% pure helium. This is called UHP, ultra high purity helium, and it costs a lot of money. Versus, are you going to fill balloons with this? No, each balloon would be so expensive. You're not going to fill balloons with this. If you buy the other helium, it's maybe 98% or something like that. Most of the chemicals we use are like 98% technical. They call that technical grade, the cheap stuff, the cheaper stuff. It's still expensive, but it's the cheaper stuff. We don't use the high grade stuff, closer to 100%. If we round this, it depends on how we round it. How many digits you want to carry this out. This we call 6 nines. 6 nines of purity, super pure stuff. Some things, they need even higher purity than that. Like silicon chips, that's not good enough. For silicon chips, you need like 100% because each little impurity means they have to throw away that chip because the circuits are getting so small. So purifying things is always a trick. So let's say this is a mixture here. This is a heterogeneous mixture. There are iron filings and sulfur. And so we want to purify it. That is, we want to separate the pure iron from the pure sulfur. And so mixture consists of elements like iron and sulfur and or compounds. And so this is called a physical separation technique. The physical separation is we're just using physical means, magnet, to remove the iron, which the iron's magnetic, so we can remove it. And then we can get the pure substances rather than mixture. And so oftentimes when we have a homogeneous thing, we try to separate it using physical means. So let's try to reverse this process. Going forward here is easy. Mix the water and the ethanol. That's easy. But reversing this is a bit more difficult. How do we remove the ethanol from the water? Can we use a magnet? No. Magnets are not going to work for this. Do you know how people do it? They heat it up. They heat it up and try to take advantage because ethanol boils at a lower temperature than water. And so they heat this up and then try to vaporize the ethanol first and leave the water behind. You know what that's called? It's called distillation. Distillation. So distillation is a great way of purifying water. You heat it up and you try to get rid of impurities. But in distillation, we heat it up to, let's say we purify this by distillation, it would be something called fractional distillation. So first we get rid of the ethanol. Then we're left with the water. And if the water is like tap water, there's a whole bunch of minerals dissolved in it. So we continue heating it up and we boil off the water. We boil off the water, we can capture the water, but the minerals stay behind. And that purifies the water.
How about salt water with the ocean?
The salt water has the salts in there, and the salts I'm calling minerals. So the salts get left behind because the salts have a much, much higher boiling point than water.
You vaporize the water.
You just vaporize the water, but you're not vaporizing the salts. The salts are residual. So you'll be left with salt residue. In fact, if you throw some salt water in a pot and start boiling it, you're going to get a lot of residue left at the bottom of the pot, salt. That's an experiment.
And then we put, what's it called? The bowl upside down and stuff like that. Inside.
Yeah, and then you can capture the water. Distillation. So this is called a physical separation here. You know, there's another physical separation. It's called filtration. And so these are the common ones here. Separation of mixtures depend on different physical properties, like boiling. And so we have distillation. Distillation means boiling off the more volatile. Volatile just means it evaporates more quickly, more easily than the other components. So we boil off the volatile component first, and then the less volatile. That relies on physical change. So here, distilled water. We're boiling off the water, which is more volatile than salt. The salts are less volatile. Ethanol, we're boiling off the ethanol first because ethanol is more volatile than water. And then we have filtration. Filtration works if you have a solid and liquid. And we have filter paper. And the filter paper can, sand and water can be easily separated by filtration. You guys have a funnel for filtration, so let's take a look at the apparatus here. This is a distillation apparatus. So we can have salt water here, and we boil the water, and we have steam. And that steam is going to go out this tube. This is called a sidearm here. And this tube has a jacket around it. This jacket, they flow cold water in. So cold water comes in, goes up the tube, and out. And this tube is hollow in the middle. And the steam goes in the middle. When it hits the cold walls of the tube, it condenses back into liquid and drips. So we can get pure water here. And so this is a common method for purifying water. Distilled water. We have deionized water. Now, deionized water isn't so energy intensive, because boiling water costs a lot of energy. Here, and it takes a lot of time. And so this costs a lot of energy to make, and so distilled water is expensive. Our deionized water removes the ions a different way. It's sort of like filtration, but it's filtration at the atomic level, at the particulate level. So,
Is there a system that deionizes the tap water, or do you have like a separate tank where you get deionized water?
There is a system. The tap water flows in up above the ceiling in the hallway. We have a whole bunch of tanks there. Those tanks contain what are called molecular or ionic sieves kind of thing. And what it does is it filters out the particles, the actual particles out of there. And so it's like filter paper, but extremely fine. And it works like filter paper in this sense. We have to replace it. It's very expensive. So our deionized water costs us it's expensive. It's like 60 cents a gallon. 60 cents a gallon is pretty expensive, compared to tap, which costs a lot less. So we try to not waste the deionized water because we've run out of money. When we run out of money, we can't use deionized water anymore. It's happened multiple times where we've run out of money and can't afford to get the deionized water. At a rich campus like UCLA, they don't have to worry about it. They have free-flowing deionized water. And then they have really expensive stuff. I used to have to use ultra-pure water. It had to be ultra-pure, like 99.9999% pure, something like that. And for my experiments. And so I would take these big, I wouldn't even use glass because glass has things that can leach into water. And so I used polyethylene, which I didn't have to worry about. So took these polyethylene jugs, 5-gallon jugs, and then walked over. And the apparatus was actually in the psychology building, like on the first floor. So I'd have to walk through the geology building and then out past the inverted fountain. At UCLA, they have this upside down fountain. This is like a toilet. So a lot of people call it the inverted toilet, or no, just the regular toilet. And then go to that and then fill it. And in that building, we have, it's called doubly distilled water. Doubly distilled water, DDW, is expensive because not only do they distill it once, they distill it twice. And then they hit it with, after that, they hit it with UV. So what goes in is deionized water. So they have all the deionized water, it's like 60 cents a gallon, then they doubly distill it. Doubly distill it is expensive because of the amount of energy that's required to boil it. You know, the apparatus is cheap. And then they cool it. This is a waste of water here. How much water do you waste, you know, flowing this condensing thing here?
Do you use it or just
Down the sink is what most people do, but you know, when you live in California, you don't want to waste good potable water. Even though that says, do you see the little tag on there? You guys didn't see this tag?
This is do not drink.
Industrial water, do not drink.
Oh, yeah.
This is not industrial water. This is tap water. The reason why this tag is here is in case somebody puts something in here and then forces contamination of the water here. So let's say somebody attached a flask in here and the flask was filled with chemicals and they left the valve open and eventually the chemicals will diffuse into the water supply, which would contaminate it. So in order to be potable water, we have to have something called an anti-backflow valve, so nothing can flow back. It only flows out. You can buy these for the house at Home Depot. You have in fact, you're supposed to buy them for the house. For your garden hose, you know, you don't want the garden hose. I know there's a lot of people shut off the garden hose with like one of these spray valves, right? But they don't turn off the main valve. Well, what happens is the stuff can leach out from the hose and get back into your house supply. And they don't want that to happen because that could poison the house supply. So you should have a anti-backflow valve at the home too. You're supposed to, but
just don't drink tap water?
Most people don't. Yeah, or don't drink tap water, don't cook food with tap water, don't whatever with tap. A lot of people do that too. A lot of people don't use tap water, or they use tap water and they filter it. That will get rid of contaminants. So they drink filtered water instead. I don't know. I drank water out of the hose all the time, and you get accustomed to the taste of water out of the hose. It has a different taste to it. Have you noticed that? And then it's like it brings back memories, tasting. And sometimes people like the taste. Like I didn't mind the taste. I thought it tasted pretty good out of the garden hose, right?
Is 99.9% pure water way better for you, like drinking wise, than it is regular?
Well, some people say no. Some people say you shouldn't drink distilled water. They say you need these minerals, like electrolytes, to replenish. So a lot of filtered water, they have a polishing filter, and the polishing filter has salts in there, and the salts dissolve and give it the water taste. Physiologically, I'm not sure. You're not going to die by drinking distilled water, but somebody did something. I'm not sure how they, because if somebody says, okay, you shouldn't drink distilled water, you want to see, okay, what evidence do you have in support of that, right? And so why are you saying that? What happens? And so you want to see some observations that are associated with that. It's like everything in science. You want something. You want to see some data that supports your hypothesis, right? Before you accept it as what's higher than a hypothesis? Theory, right? And the problem with theory is it's so misused. I was listening to a talk, and the person was talking about theories, but really what they meant was not theory. They really meant hypotheses, because things haven't been fully debated out, and resolved in that sense. But there are established theories right now. in the physics world, like the Standard Model. Have you heard of that? The Standard Model of what things are made out of, like quarks. I'll get to you in just a second, but in other things. So there have been some other things that have been proposed. But for us, that's not going to impact us, because what is the theory for chemistry?
Observation of nature.
No, I mean, what is the name of the theory for chemistry? The scientific method led to the development of the theory of chemistry. We'll talk about that later. This is, okay, think about this. You have to think about this in terms of, this is why I remember what I mentioned is if somebody had allowed me to record their lectures, then I thought that's an easy A class. It's an easy A class because even though my memory is weak, if I review it every day, I'll get it. And so if I had mentioned theory a long time ago, I would have read it a number of times. So I would, the theory of chemistry, I would have. But if you had never had it written down in the first place, then there's no way. So if a question popped up on a test right now, what is the theory of chemistry? And I had just mentioned it once in class, then you either have it or not. And the people who have it are going to get those points. And so that's helpful if you have it. But nobody remembers? Nobody can recall it? This is just a recall question. You don't have to have any advanced knowledge. Quantum mechanics, good. That's it. But you need to recall it faster because at UC, they test not just on content knowledge, not just on your problem-solving capabilities, but they also test on speed. I used to hate that. I used to hate not being able to finish tests, and tests that were designed to be too long for the given amount of time, because it was a sprint, and I just didn't like that. And so you want to build up this speed if it's possible. So if somebody asks you the theory of chemistry, mechanics. But if you never had it written and you never reviewed it, then that's one of those ones you just left blank. Figure it out later. Although, of course, since it's the theory of chemistry, we're going to talk about it a lot more. All right, this is filtration here. We have filter paper. What we do with filter paper is this, and this is something I never really understood. And I did this too. You take, and this is just a flat circle. You fold it again into a quarter. And then you'll open it like this. So you have 3 sheets on one side, 1 sheet on the other, and then you tear up a corner. And I never understood why you tear off a corner. So I always did it, and then I figured, I'm going to try it without tearing off the corner because it's just an extra step. And so I did it without tearing off the corner, and I didn't notice any difference. So now I never tear off a corner. But, somebody told me to tear off a corner, I just said, okay. But I never asked them why. This is in science, you want to know why you're doing that, What is the data that supports tearing off a corner? But
Can you Google it to find out why?
I can, but, I just did it myself. It's easy enough not to tear off the corner and then compare the two, and there was no difference. Maybe there is a difference. I just didn't notice it, so I stopped doing it. But that's just my personal observations. Anyway, we can separate sand and water here using gravity filtration. There are other types of filtration too. This is an example of physical separation. All right, when we have pure substances, we try to separate things into pure substances. So if I have sand and water, I try to separate into pure sand and pure water. Is sand pure or is sand a mixture? Yeah, sand is a mixture. And so I try to separate the particles of sand. Have you looked at sand, the different particles in sand? Yeah. Probably the most abundant is quartz. Yeah, and sand. And so I try to separate out quartz and then other components. Less. That quartz, people separate it out all the time because you know what they make out of sand? Glass. Yeah, so they separate out the quartz and make glass. And there are lots of different compositions. There are thousands of different compositions of glass, but we have pure glass. Pure glass is called quartz glass. It's silica, and it's expensive. It's extremely high temperature.
Obsidian glass too.
Obsidian's glass, and it's quartz based kind of thing, but it has other stuff in it. All right, we have different types of pure substances. A pure substance could be an element. It has fixed composition. This is the composition of an element. Example, silver. Or compound, like water. Or sugar. We have many different kinds of sugar. The table sugar I'm talking about is sucrose. Sucrose is fixed composition. Sucrose is 12 carbons, 22 hydrogens, and 11 oxygens. So when we have a mixture, we try to separate this into pure substances, either pure compounds or pure elements. The compounds themselves are made up of two or more elements bonded together. However, they're difficult to separate. So let's say I have water and quartz. Well, actually, quartz would be here. Water and quartz, two different compounds. And those would be pure. But what I can do with these compounds is I can try to separate. Do you know what water is made up of? Yeah, H2O. And so hydrogen and oxygen, but can I filter out the hydrogen from the oxygen in water? No. Can I distill out the hydrogen from oxygen in water? No. What I have to do is I have to separate that by chemical means. There's a way to separate the hydrogen from oxygen. One chemical mean is by using electricity to do it. We can use electrical energy to do that. If you have a 9-volt battery, okay, well, let's see if it'll do that. Battery electrolysis. Maybe it'll still find it. Yeah, here it is, correctly spelled. Let's find a short video.
No wonder Steve Garvey wants to block Biden and Pelosi's progressive agenda and supports building Trump's border wall. Garvey stands for Trump.
Both times he was the best person for the job. I voted for him twice.
Steve Garvey is too conservative for California.
Okay, let's make some hydrogen. So we know this is water, this is plain water.
There's some water here.
H2O, hydrogen and oxygen.
This could
molecules
be
have
pure
hydrogen and oxygen. We're going to separate them into hydrogen gas and oxygen gas. Okay, so here's what we need. Water.
Okay.
Now I'm going to take this cup and I'm going to take two of these metal thumbtacks. They want to be metal on both sides. And I'm just going to poke one in.
Make what are called electrodes.
There, popped it through. Now I'm going to take the other one and put it near it, but not touching.
Let me speed this up.
It should.
Speed it up. Let me speed up.
And we're going to do electrolysis on the water. So I'm going to take the water and pour it in. Now, if normal water
very slowly in pure
doesn't,
water.
if it's really pure water, it's not going to conduct electricity. And notice, look, it's not even leaking. See, because the thumbtacks is poked right through. So you can add something in there to make it a better conductor. Here's just normal table salt. That works well. Baking soda, that works really well too. So I'll just put some baking soda in there, which works a little bit better. Okay, so now I have baking soda. And now I'm going to take I'm going to hold it up here so you can see it. Let's look. Okay, watch the two things. And You can see the bubbles coming off, right?
Do you see some
Both of them have bubbles. One of them is hydrogen and one is oxygen. The one connected to the negative lead of the battery is going to be your hydrogen. So you could then take, you see the bubbles up on the top, you could collect those into a bottle, and then you'd have hydrogen.
We should form
You could collect the oxygen too, but there's already oxygen in the air. So see. So you can see it's really going well now.
Can you tell me which one's hydrogen?
That's pretty cool. So you're just making, you're taking this water, separating some gas, the water into, just making, you're really going well now. That's pretty cool. So you're just making, you're taking this 9-volt battery, collect those into a bottle, and then you'd have hydrogen. You could collect the oxygen too, but there's already
The one
oxygen
on the left appears to be making more bubbles
in the air. So see. So you can see it's really going well now.
Do you see that? The one on the
That's
left.
pretty cool. So you're just making, you're taking this 9-volt battery.
And so that would be the hydrogen on the left. So is that the small or the big? Let's see the orientation of this battery. This is small. Or the big one. This is the big one, that's the small one, let's say. So the hydrogen is being produced here. You see that? And the oxygen is being produced here. So do you know which one's positive and which one's negative? The right one. This is the positive. So the oxygen is being produced at the positive, and the hydrogen is being produced at the negative. Well, anyway, that's the. This is an example of a chemical separation, because here we no longer have water. What we have is hydrogen, the element, and oxygen, the element. That's a chemical separation. And so compounds have to be broken down chemically here. The chemical separation technique, sometimes it has to involve a sequence. So some compounds decompose into other compounds, and then these compounds might decompose into other compounds or elements. So there should be one more arrow here. You know? So this is kind of weird. And so we should be able to take these. So some compounds will break down into other compounds chemically. And these other compounds eventually can be broken down into elements. So the final point is we're going to have elements. Everything's made up of elements. So these compounds will just go over here to here. And so when we have something like a mixture, we can separate the mixture into what we call substances. Substances are compounds or elements. This is substances versus mixtures. And so substances versus mixtures. And then the substances, which are compounds or elements. Elements can't be broken down further, but compounds can. Compounds can be broken down into other compounds by chemical means or straight to elements like water. And these other compounds eventually will end up at elements. So everything's made up of elements. Here. That's the basics. Okay. Let's see. Let's take a break here. We'll take a break for 15 minutes. Where the homework was. So the homework is here. If you click here, and then click this PDF here. I thought the 7th edition was going to be different, but the 7th edition is the same as the 6th edition, so there's no difference in the numbers. You just do these numbers here. That's a lot. So don't wait until the night before the test to start the homework. Get started early. I know there's people already doing chapter 3 homework, so that's good. To get a head start on that is good. You know. So these are the homeworks. Yeah, I'm going to post a link on Canvas. And that's going to be on week 4. There'll be a link to upload the homework. I'm going to collect the homework on week 4.
Can I bring it in physically or no?
You could bring it in physically if you want. Check it off. The day of the exam. If you don't want to scan, it's a lot of good stuff to scan, so paper's fine. So where is the quiz? I didn't make a separate page for the quiz. This happened on Wednesday, so I posted the lecture slides. It was a slide that I posted on the board. That's where it is, right here. So this is the quiz. I haven't uploaded the YouTubes yet for week 2, I think. Yeah, I still need to process those, so I'll upload that today or tomorrow. All right, so you can work on that. We'll have some time at the end of class. You can work on that to resubmit it. You know. Let's wrap up chapter 2 here, and then let me start up chapter 3. If this were 24 karat gold, would that be a? That would be pure, yeah. And would that be a pure substance, or? Yeah, that would be a pure substance. But a substance can either be an element or a compound. So if that's pure gold, it would be a pure element. Yeah. If this were, let's say, 18 karat gold, then it would be a. It wouldn't be 18 karat gold. Has variable composition depending on who made it. You know, I think a lot of people might make it at 75% because they can save a lot of money that way, right? Maybe. Or maybe they make it at 79.95%, depending on how precise they would be. And so it would be a mixture of what? Gold and silver. Yeah, gold and silver. And then how would you separate the gold from the silver? Let's say you wanted pure gold and pure silver. How would you separate it? Yeah, probably by their melting point. And that would be an example of a chemical separation or a physical separation? Physical separation, okay. This is pure silicon here. I'm making silicon chips, which doesn't have anything. This would be lead, but this is heterogeneous also. There's a little range here, but if you just look at the lead weight itself, that would be pure lead. But pure lead's kind of expensive, so it's probably like 98% lead or something like that. Probably not 100%. What's this? The lead. This is not lead. This is graphite, which is pure carbon. Graphite is pretty easy to get at high purity. It's just because of the way it forms. This is supposed to be pure copper here. This is supposed to be what? Pure gold. Together. This doesn't look. This looks like. This is actually heterogeneous if you scrape it. You know what the coating on the bolt is? Steel. This is steel. Underneath this is steel, but this has this more silvery coating on it, and the steel doesn't have quite this color. Silver. It's not silver. Nickel. It's not nickel. It's zinc. Zinc is a common coating. Do you know why they coat these things like steel, iron with zinc? No, not because of its look. It's to prevent rust. Rust is a chemical process. And the zinc, they're using the zinc as a sacrificial antioxidant. So zinc you can think of as an antioxidant for the steel or the iron. But the antioxidant doesn't last forever. Eventually, all the zinc gets eaten away, and then the bolt itself will start to rust. This is called galvanizing. Galvanizing, we coat iron and steel with zinc, and zinc is a great antioxidant for iron. Over here, this used to be 100% pure copper, but not anymore. Do you know what it is now? It's it's copper coated zinc, and so underneath this we have zinc. Except zinc corrodes quite easily, and so what you have to do is the copper has to form an impermeable layer. So if the copper protects the zinc won't corrode. But if the copper has a chip in it or scratch in it, then the zinc underneath that can corrode. So have you ever seen a hollow penny? A hollow penny is where they put a little nick in there and then they get something to corrode out all the zinc, wash it out. Usually acid will corrode it out. You don't want to eat this. Kids who eat pennies get zinc poisoning because if their stomach acid will start to corrode the zinc inside there, and they get too high levels of zinc. We need a little bit of zinc for our bodies, but not too much. Here, these are all elements. Over here we have compounds. Chalk is mostly what? Chalk is mostly like calcium carbonate. What other elements? Drain cleaner. Drain cleaner is mostly sodium hydroxide. We have baking soda, sodium bicarbonate. This is quartz with silicon dioxide. I don't know what these are. Rollades is antacids. I don't think rollades are pure. They might be pure. So anyway, pure substances, we have a fixed formula, He. For elements, it's pretty easy. Except for the diatomic. You know the diatomic elements? Zinc is not a diatomic element. No.
Is it hydrogen, oxygen, chlorine?
Hydrogen, oxygen, chlorine, that's 3. Iodine. Bromine. Not bromine. Fluorine. One more. Well, iodine's already been said. Nitrogen. And so those ones we write as like O2, with a subscript, N2. Those would still be pure, etc. For compounds, we'll have a more complex formula. So we could have pure baking soda. Pure baking soda would be NaHCO3, sodium bicarbonate, call it. We have HCl. HCl is called hydrochloric acid, or in pure form, hydrochloric acid is actually HCl mixed with water, so it's a mixed acid mixture. But in pure form, it's a gas, and we call it hydrogen chloride gas. Water, we have different names for water. This is also called what? DHMO. Do you know what DHMO stands for? Did I talk about that, DHMO? That some cities had banned DHMO or planning to ban DHMO, especially in California.
Is it water? Is that the methane ovens you were talking about?
No. This is different. DHMO stands for dihydrogen, 2 hydrogens, monoxide. Mono means 1. 2 hydrogens, 1 oxygen. Dihydrogen monoxide. And so they said dihydrogen monoxide is toxic in high quantities. Did I mention that before? Yeah. DHMO. So there are some cities that plan. Lisa Viejo is one in Southern California that went until somebody figured it out. It was a prank, and then they didn't finalize it, but it was close to being finalized. So. and others. But it's water. But nobody calls it dihydrogen monoxide. That's why it fooled so many people. You know, they said water, and everybody would have known. This is called barium chloride. This is not called barium dichloride. Do you know why this is not called barium dichloride? They call this maybe dihydrogen monoxide. But you know, the reason is because barium has a fixed charge. Do you know what the charge on barium is? Look at the periodic table and find barium. It's not negative. Find barium. It's in what group? 2, which means its charge is 2 plus 2. And then chlorine is also a fixed charge. What's the charge on chlorine? -1. So if you have a +2 and each chlorine's -1, how can you get the charges to balance? Have 2 chlorines. And so there's 2 chlorines and -1. So if somebody says barium chloride, then you know how many chlorides are on there because barium's +2, chloride's a -1. There's got to be 2 chlorides for every barium. However, something like this is a little bit confusing because in addition to water, which is H2O, we also have dihydrogen dioxide. What was dihydrogen dioxide known as? Hydrogen peroxide. And there, okay, city can ban hydrogen peroxide, that's okay. You know, but you'd have to get rid of all your hydrogen peroxide in the refrigerator though. Do you store your hydrogen peroxide in your refrigerator? Or does anybody buy it anymore? Yeah. People still buy it? Yeah.
I don't store it in my fridge either.
We always store hydrogen peroxide in the fridge. Do you know why?
Will it die if you don't?
Because it slows down the decomposition. It decomposes chemically into water and oxygen, and so it slows it down and makes it last longer. You know, that's all. And so all our hydrogen peroxide is in the fridge here. And I have hydrogen peroxide in my house. I have it in the fridge. If you leave the cap off, not very long. You know, a couple of days will go flat. You know, it's like if you have carbonated water and you leave the cap off, and a couple of days later or a day later, it's flat. Hydrogen peroxide's the same. If it's contained, it'll last a long time. It'll last a long time, whether you refrigerate or not.
Is soda like a good example as well? Like example like Coke, you just leave the cap off, it goes flat.
Yeah, it'll go flat. The same thing with hydrogen peroxide. You leave the cap off, it'll go flat. But there's one other thing that'll impact hydrogen peroxide that's light. You know, if you have soda, you can have it in a clear bottle. You don't care about it being exposed to light. But hydrogen peroxide, if you shine light on it, it'll decompose it as well. That's also a chemical decomposition. So that means that these are more variable charge. I know oxygen likes to be -2, but in hydrogen peroxide, oxygen actually turns out to be a -1 because hydrogen is a +1. So we can use these things to kind of figure out certain things. But anyway, in the next chapter, we're going to be talking more about these. So atoms are the smallest particle of an element, and a molecule is the smallest particle of a compound. There's actually, there should be another one here. That would be formula unit. Formula unit is the smallest unit of either a compound or an element. And so let me add that here. Formula unit is a generic term that can be used for anything. Not everything forms molecules. Name one thing that doesn't form a molecule. Salt, yeah. And so this would be the smallest unit of whatever. So formula unit of water would be a water molecule. However, formula unit of salt would be 1 sodium and 1 chlorine. Smallest unit. And so formula unit is a generic term because not everything forms atoms and not everything forms molecules. Some things like salt. the smallest unit would be 1 sodium and 1 chlorine, but it doesn't form a discrete molecule. Let me save this out. Okay. Pure substances have fixed composition. So this is a law of constant composition. Water always has the same composition. Pure water, tap water is a mixture, but pure water always has the same composition, regardless of its origin. And that's the law of constant composition. Mixtures don't. Mixtures will have variable composition. How did they figure it out back in, back pre-Dalton days? Pre-Dalton days, they figured it out based on mass proportions, And so, in other words, water always had the same mass ratio. Post-Dalton days, post-Dalton, we know things from atoms, so 2 atoms of hydrogen, 1 atom of oxygen, is H2O. Pre-Dalton days, you have to figure out how many grams of hydrogen, how many grams of oxygen, and that ratio is fixed. Does that make sense? So we have these mass ratios. In other words, mass percentage. Did you know that another way of calling water is it would be H11O89? You know what that means? H11O89? That means 11% hydrogen, 89% oxygen by weight, by mass. Oxygen weighs a lot more than hydrogen. And so by weight, it's different, it's composition. And so these mass proportions are different than what we're used to. What we're used to are the atom ratios. Atom ratios are so much easier. This law of constant composition is one of the reasons why people believe Dalton. Why would you believe Dalton? Well, one of the reasons is the law of constant composition, because if matter were infinitely divisible, then can't you just have a smidgen, just a tiny, infinitesimally small extra bit of hydrogen or extra bit of oxygen in your water? If it's infinitely divisible, then yeah, we can have just a little bit extra. It's hard to get it perfect, isn't it? Let's say you have a recipe, it's asking for, 1 cup of sugar. Do you get it exactly at 1 cup, or do you just get it close enough? And is that powdered sugar, or is that granulated sugar, or what is that? Sugar is a solid. So some people like the corn syrup, which is just a liquid sugar, right? But there was some interesting observations with corn syrup over COVID. Did you hear about that? Like, you wouldn't think it, because people like when I was like in middle school or something. My friend's mom made these Rice Krispie bars that were delicious. I thought, so good. I wanted to get the recipe. So I got the recipe. It was like corn syrup. And it had to be a certain kind of corn syrup. It had to be like, I forgot the name. It was Craco or Crano corn syrup or something like that. Yeah, Caro, that's it. And so I used to make that and eat those all the time. But then some of these recent observations on corn syrup would make you rethink it, because I thought, oh, that's overhyped, this whole thing. It's like this paranoia. It's being a little bit too extreme for me. But the data, this is data from Dr. Schwelt at UC Riverside. That guy's board certified in like five medical disciplines. But he was reviewing some of the experiments that they had done with corn syrup and blood. It was interesting, blood clots and that kind of stuff.
What's so bad about corn syrup?
Just take a look at the data. I used to hear people say, "Oh, stay away from corn syrup," but they never gave me any kind of reason to stay away. So it's like tearing off the corner. You know, eventually you go, "Oh, why?" I like the taste of corn syrup. I'll just keep eating it unless you have some adverse data. Well, there are some studies that show some adverse data, which surprised me because I thought sugar is sugar. It doesn't matter what the form is. It's just sugar.
I don't really remember if you ever answered the question on how Dalton proved that atoms exist.
Well, this is one of them because the other argument is this: if you believed in infinitely divisible matter, then why it would make sense that when you have infinitely divisible matter, it's hard to get the proportions just right. Have you ever tried to do that? Have you ever tried to get a mixture perfect down to the single atom? Because at the level we work at, let's say you had to get the mixture, and you go to the, let's say you needed 1 trillion particles of sand for every gallon of water. So it's just a little bit of moist sand, maybe barely any water in the sand. But can you imagine getting that mixture just perfect to the exact number of sand particles? What if you had one extra sand particle? That screws up your ratio. Or you didn't have enough, like one particle less. So the argument goes like this. If matter were infinitely divisible, then how come you can't have one extra sand particle? It's infinitely divisible. These particles are much smaller than a grain of sand. And so how small are they? They're way smaller. And so a trillion is nothing. That's a huge number. Or a huge particle, in other words. We're talking about infinitely divisible. So the argument goes that the camp that believed in infinitely divisible, they could you come up with a good, reasonable, sound explanation why that ratio can't be one tiny, this is so tiny, it's not even like a grain of sand, extra piece in there. And if you could have one little tiny extra piece, why can't you have multiple tiny little extra pieces in there and screw up the ratio? And why doesn't the ratio change a little bit? Do you see the argument? If you're arguing for infinitely divisible, or you don't see it? You don't see it? You don't, okay.
How did he prove it?
How did who prove it? Dalton?
How did he prove it to everyone else?
Mass, no?
How he proved it is this. The law of definite composition.
Mm-hmm.
This is how he proved it. How he proved it was that matter is conserved. That is, the number of atoms number of atoms that you start with and the number of atoms that you end up with are the same. And so the proof goes like this. If you were to argue the point of infinitely divisible matter, then how does this fit in? How do you always get the same ratio, 2 hydrogens for every oxygen? Why doesn't that ratio vary a little bit? And so how would you prove the counter argument that matter is infinitely divisible? You see this? And so the situation is, which one is a more reasonable explanation that matter is not infinitely divisible? Having a finite particle, which is easy to see, hydrogen's always going to be H2O because the smallest particle of hydrogen, you take 2 of those, and the smallest particle of oxygen, you take 1 of those. But what's the smallest particle of hydrogen if it's infinitely divisible? Does that click or it doesn't click at all? So, but the thing is, this is Dalton, during Dalton's time, this is how he proved it. Is that like a slam dunk in proof? Do you think that's easy to convince people? And so this is why, and the point of this is like this. When you're working in science, you want enough proof. You want enough proof that you can silence all your critics. But in order to get enough proof, you need an infinite amount of time to generate that proof. But there isn't an infinite amount of time to generate the proof. So this is why scientists do this. Scientists are always doing this. They're gathering the data and then using the data in support of it. Some people prove things some people will prove things by not real proofs, but by attacking, the other side. And they're attacking the other side not based on supporting observations or supporting evidence, but they're attacking the other side based on other things. And so this has been happening recently. What's been happening recently is we're veering away from science and veering more towards censorship. And censorship in science is a really bad thing. And so what should be happening is open debate. But the kind of the slam dunk here is that theory should be able to do one more thing. And what should theories be able to do? This would be the kind of the slam dunk in evidence, because law of constant composition wasn't enough. What was the other proof? Does anybody recall? Theories should be able to do two things. What should theories be able to do? Predict. That's the second thing. Theory should be a fundamental explanation, and theory should be able to predict. What did Dalton's law, or Dalton's, not law, but Dalton's theory predict? One more thing that Dalton's theory predicted, and this was the convincing. I mean, a lot of people won't believe this because, sure, there must be some underlying reason which is unknown why hydrogen always is 2 and oxygen is always 1, no matter if matter is infinitely divisible, but it just makes more sense with atoms. But what was the prediction that Dalton did? Did anybody write it down? We can use, there are two ways that laws can be derived. What are the two ways that laws can be derived? Empirically, or by theory. And so what was the law predicted by Dalton's atomic theory?
The law of conservation of mass?
No, that was the law that was used in developing Dalton's atomic theory. No, the law of conservation of energy wasn't it either. It was another law. I didn't write it down. I just said it verbally. I just said it verbally because we're going to do this one more time when we get to Dalton's law.
Law of constant composition?
That was one of the laws that was used to support Dalton. So that was one part of the proof. But the other part of the proof was the prediction. This is what's going on a lot in theory right now. In theory right now, like, for example, like string theory. Have you ever heard of string theory? String theory is difficult to support because what kinds of predictions can you make that are observable with string theory? So there's nothing you can really predict and then observe, right? To further solidify the proof. But with Dalton's atomic theory, he was able to predict a new law and then test it. And the new law that was tested I talked it in relation to water and hydrogen peroxide. Does anybody recall? Water is always H2O, and the hydrogen peroxide is always H2O2. And then I asked, is it possible to have H2O 1.5? I don't know if anybody wrote that down or not, but do you recall that? I asked H2O 1.5 or maybe H2O 0.5. And then, no, those aren't possible because that would violate the law of Yeah. Okay, so this is another advantage. This is why I thought when they allowed recordings for the film class, I would never miss anything, because if you miss something, then there's nothing to study, and there's nothing to study, and you get hit with it. And they'll hit you with anything, whether you think it's fair or not. You'll get asked, certain things. It was the law of multiple proportions. The law of multiple proportions was what Dalton's theory predicted. In Dalton's theory, the law of multiple proportions says that the elements combine in simple whole number ratios. So, like you aren't going to have 1.1 hydrogens for every oxygen. They're going to be in simple whole number ratios. Now, if matter were infinitely divisible, then why would we have a law of multiple proportions? Because if matter were infinitely divisible, we can mix them in any proportion we want. Now, if you're taking the counter argument, what evidence do you have in support of your counter argument that we can have any ratio? Because when people they analyze these things, and this is pre-Dalton time, they analyze it for the weight percentages. So if you look at hydrogen peroxide, it gives you a certain weight percentage of hydrogen, a certain weight percent of oxygen, and hydrogen peroxide is always the same. That would be the law of constant composition. Now, the law of multiple proportions would be the ratios. It's a 2-to-1 ratio, or it's a 2-to-2 ratio, but it's nothing in between. And so based on those two pieces of evidence, that's it. That's the proof. Now, would that convince everybody? Probably not everybody was convinced. And there are still non-believers in atoms up to a certain point. But nowadays, there's overwhelming evidence. And but the situation is you think, okay, now we have modern instruments, but there's still a lot of Daltons out there. There's still a lot of Daltons. Like the person who developed string theory, he's trying to convince other scientists that this is the correct model of the universe. And then there's other people who are convinced of the others. And so this is still going on. This scientific debate is still going on a lot of things. The scientific debate is simple as, what's the origin of coronavirus? That's still, there's still people arguing both sides of that, And so that's a good, healthy debate. Although, that's been censored. Like one side of that's been totally censored. He convinced enough people that it went from a hypothesis to a theory. And so theory needs this. Theory needs to be a fundamental description of the observations, the laws. It should be able to predict, and it should have widespread acceptance. Hypothesis doesn't. A hypothesis needs no widespread acceptance. In fact, I saw a great video on this, which I was thinking, I should show this. About this, because theory and hypothesis are so frequently confused that I thought this was a pretty good explanation of the difference between a theory and a hypothesis. And let me show it to you.
Congratulations. Your mijo and your money are off to college, and you don't know how you're going to pay.
Physics can get extremely complicated. While the mechanics we experience in our daily lives are relatively easy to understand, it gets really, really confusing when we examine things either on the smallest scales or the largest ones. Quantum physics and astrophysics are right now as far as public interest is concerned, but ideas within these realms are frequently misunderstood. So let's have a look at some of those, shall we? The word theory gets bandied around a lot, but it's frequently used incorrectly. This misconception isn't limited to physics, but rather extends through all of science. Many terms you have heard described as theories are actually hypotheses, and there is a very important scientific distinction. A hypothesis is just an educated guess. They often represent the best possible answers that we have available at the time, but it is still just a guess. These ideas are either untested or untestable.
Try clicking with that simulation.
All right, sorry, this is not very loud. I don't know what's wrong with this audio, but this is going to come from my computer. Can you hear it? Okay, so in Gall's case, we have the law of multiple portions. So what people did was they tested it, and they looked at all the compounds, and all the compounds had simple whole number ratios. They couldn't find compounds that had variable ratios, and so this is the evidence and supporting the theory. Now, that amount of evidence is very weak compared to the evidence we have nowadays. I mean, we can manipulate individual atoms. Have you seen the this was back in when STM was first developed, but there was the atom person. I guess they called it the atom man, but I guess nowadays we call it the atom person. And this was, or the IBM logo, or the atom boy. They made a little movie. On the volume. Actually, we don't need the music. But they manipulated individual atoms on the surface. So this is back when IBM originally these tunneling microscopes here. Keep this sound. A cluster of atoms, and then they can push the atoms around using the tip of the microscope. Now, if you take those atoms and try to break them into smaller pieces, you couldn't. They'd lose their chemical identity. And so that's, if Dalton had proof like this, nobody, he would have had an easy job. You know, when you're getting, it's like when you're getting your PhD, you know, if you have slam dunk evidence, that is, it's irrefutable evidence, it's easy. But what most people have is they don't have irrefutable evidence. They have some evidence that supports their point, and they have to argue their point. You can't wait forever to have irrefutable. If Dalton waited forever, then he wouldn't have lived to this day to see this. So he had to prove it just based on the law of constant composition, the law of conservation of matter, in order to develop the whole concept of atoms, and then the proof or the testing came in the law of multiple proportions. And that's about the extent of it, but it had garnered widespread acceptance because it seemed to make the most sense. It seemed that that was what had supported it. Now, when you say prove, that's very difficult in science. How long do you want to wait? Do you want to wait till infinity to prove something? You have to get as much evidence as you can. Like, how can you prove one way or the other? Did the coronavirus originate from bats that went to pangolins that went to humans? Or, you know, the proof is, and so what we do is we get as much supporting evidence as possible, because proving things like a mathematical proof, do you know quantum mechanics hasn't been proved mathematically from fundamentals? Quantum mechanics is the theory that we use, but it is taken as postulate. Do you know what a postulate is? A postulate is you take it without proof. And a lot of things, like you might have done proofs in geometry or proofs in math. You know, we don't have that level for some of this stuff. And so that's the extent that we have it. Now, does that make it useless? No, it's still very powerful because, you know, without quantum mechanics, we wouldn't have MRIs. MRIs were a prediction based on quantum mechanics, you know, MRI for imaging. And actually that won the whole, this is called magnetic resonance, and MRI stands for magnetic resonance imaging. And the whole concept of magnetic resonance is one of the predictions that was unforeseen by quantum mechanics that was proposed. The first group of physicists to propose magnetic resonance, they went out to test it and observe it. But the electronics were too weak. They didn't have powerful enough amplifiers. This happened in the 1950s. And then in the 1960s, it's 10 years later, the amplifiers became much more powerful. And so it turned out it was another group of physicists that went out and tested it with more expensive and more modern electronics, and they were able to observe it. And this is one of the things, the bad things about the Nobel Prize. Who won the Nobel Prize? Who won the Nobel Prize should have been both groups of physicists. The original physicists that proposed it but were unable to observe it, and the physicists that were able to observe it but just had more sophisticated electronics. But do you know who won the Nobel Prize? It was the physicists who had the more updated electronics. The physicists who originally proposed magnetic resonance were completely from the Nobel Prize. So the people who know about magnetic resonance and that, I used to work in magnetic resonance, and I used to use this kind of stuff. The physicists that know thought that was one of the bad things that happened in the Nobel Prize. But it's the same thing, Dalton's got to argue these things, like all scientists have to argue these things based on what evidence they had, and the original group of physicists didn't have evidence to support their hypotheses, whatever, their law, their observation that they predicted with the theory. So everybody wants irrefutable proof in science, but we have just observations, and we have this collection of observations which we try to prove things. It's interesting because you hear people make these claims, like, for example, the body is pretty complex, you would think, and like inside the cell, do they know every single thing inside the cell, or are there still some things that they don't know, that they haven't identified, that are present in the cell that they just don't know? You would think they know everything because you see pictures in biology books of the cell, but they predict based on the mass. It's like dark matter. There's some mass out in the universe that's got to be there because of the way gravity works. Well, based on the mass of the cell, there's some stuff in the cell that they haven't identified. Did you know that? And so they predict that they know about how much matter is there. They just haven't identified what the compound is, or composition, and they know something about the function of it. But the cell is a complicated mixture. It's hard. This brings up the story. A lot of science is still empirical, and so the University of Michigan, they're looking at the effects of electric fields. Electric fields, they put a positive, like the battery, they put a positive electrode in there, like the thumbtack, and a negative electrode. And so they put these like thumbtacks in, but thumbtacks are too corrosive. And so you know what they use? They use platinum. So if you put a platinum thumbtack and platinum, one of the properties of platinum is it's like gold. Platinum and gold are called Nobel metals. Gold is used in a lot of electronics. You know why gold is used in electronics a lot? It's a great conductor, number one, and number two, gold doesn't corrode. Well, platinum's the same. Platinum is very non-corrosive, and so platinum is like gold; it retains its luster. Gold remains shiny, whereas if you had a piece of iron, is that going to remain shiny? No, it's going to rust. And this is why you need to protect iron with zinc. That's called galvanizing zinc. But with gold, you don't need to protect it. You don't need some antioxidant. It's not going to oxidize. Well, what this group of researchers did at the University of Michigan is they put 2 platinum wires into a petri dish of tumor cells. And then they cranked up the battery voltage. It's like a voltage but they can control it, 9 volts, 10 volts, whatever volts they want. They just turn up the dial. And what that does is it creates an electric field. And so the first thing they noticed was, oddly enough, the platinum started to react with the culture medium. And so it was generating a chemical or something. There was a chemical change that they saw because the platinum started corroding, and then whatever chemical was produced killed all the cancer cells. And so they thought, wow, something reacted with the platinum. But the thing is, what that compound is, they generated so little of it, right, that to separate it would have been insanely difficult. Because if you have a culture medium of cancer cells and you want to separate that into its individual components, that is individual elements and compounds, what are you going to do? Filter it? Distill it? How are you going to separate it? And so it turned out to be a horrendous task to separate that compound, and there's so little of it generated because platinum is fairly unreactive. So you know what they did? This is an amazing story. You know what they did? They went to there's a whole bunch of chemical manufacturers, and they looked up every single platinum compound that they could find, and they bought it. And so they bought every single chemical compound that was available from the manufacturers, and they tested each individual one. And you know what? They found it. They found it. And that compound, cisplatin, And it turns out it's just a platinum with 2 chlorines attached to it. It looks like. And it has these things, which are ammonias, NH3s. So it has 2 chlorines and 2 ammonias. And they didn't care. They knew it worked, but how did it work? You know how this thing worked? The weird thing is, what happens is this is flat like a pancake. And they finally figured out the mechanism, how this worked, because, you want to know how things work. And how things work are based on the structure. Well, it turns out the structure of this is very important, because there's one more form of this. The other form of this is called transplatin. And so they could buy cisplatin and transplatin from the manufacturer. But when they look at the transplatin, it looks a little bit different than the cisplatin. Transplatin didn't work. Cisplatin worked. Do you know how it worked? How it worked was that this pancake molecule gets stuck in the groove of the DNA and prevents replication. And so what happens is the cancer cells can't grow anymore. And so this turned out to be one of the most successful chemotherapy. Chemotherapy is a chemical therapy agent for treatment of cancer. And so I think especially breast cancer, and it's been in use since the 1970s. So this is one of the most common chemotherapy treatments for cancer. But how it was developed was so interesting, because originally they were thinking of just trying to put electrodes in there and then making an electric field that is a positive and negative difference there. And so this is one of these serendipitous observations. Penicillin was another serendipitous observation, where spores contaminated cultures and ended up killing the bacteria cultures. But isolating it is different. Penicillin was a little bit easier to isolate than something like that, but still, it's a tough thing. I mean, how do you separate this from everything else in there? It's a very complex mixture. Separating mixtures is a huge topic in science, and there are a lot of sophisticated instruments in separation. We haven't even talked about chromatography is one of the big ones, and it's not here, but it'll pop up a little bit later. But anyway, let me finish off chapter 2, at least get this done. A lot of these things, how does this get stuck in the groove? How is it sticky? This is not sticky, this is sticky. And how it's sticky is due to this. When you look at electrostatic forces are the attractions between opposite charges. And so if we have a positive and negative attract, but 2 positives repel and 2 negatives repel. So like charges repel, unlike charges attract. This is called Coulomb's law, and these are Coulombic forces, electrical forces, or electrostatic forces, Coulombic forces. Coulomb's law puts this into quantitative, rather than qualitative. This is very qualitative. Coulomb's law we should write down here because it's important. The force of attraction or the force of repulsion depends on 2 things. It depends on the charge of A and the charge of B, which we call Z. So Z is the charge. The higher the charge, the stronger the attraction. So if we double the charge, we're going to double the force. If we double A and double B, we quadruple the force. And it's also the distance between the charges. That is the distance between the center of the charges. So I'll write this as D, and it's inversely proportional to the distance squared. So the force drops off quite rapidly with distance, because it has a nonlinear term that is a squared term. So as the distance grows, the force gets incredibly weak, but as the distance shrinks, the force gets bigger. So there are 2 things: the magnitude of the charge and the separation, the distance or the size. I call this the charge density. So we'll be looking at the charge density later. As far as the force, Coulombic force, and electric force. This is called Coulomb's law. This is one of the laws you learn in basic physics. This is not a physics class, but this one's really important because, quantum mechanics comes from physics as well, but it's important for chemists. So this is Coulomb's law. Coulomb's law, this is empirical. This was not derived from theory, but I suppose it can be derived from theory.
What's that? Empirical?
What does empirical mean again? Yeah, derived from observation. Right. That's what it means. Here's Coulomb's law in action. When you rub things like this, if you rub this silk on this plastic, some of the electrons aren't tightly held, and so you can build up or remove electrons. So when they rub the silk, it's removing some of the electrons, which are negatively charged off the rod, so the rod ends up becoming positive. So what they do is they touch one of the balls, and it becomes more positive. And so both of these balls are positively charged. These are like little cotton balls, and they repel each other. So a positive and a positive repel. Whereas if they use fur, then that imparts a negative charge to this rod here. And so some of the electrons get transferred from the fur to this rod, and then they can make one of these balls negative. So if they make one of these balls negative and the other positive, then they come together like this. So this is essentially Coulomb's law. And the more charge there is, the more the force and the distance is going to make a difference. Because if you separate these by too far a distance, then they're going to have enough force to come together like this. Getting back to predictions, so I was listening to let's say the some of the mRNA vaccine. I got the Moderna vaccine myself, but they're saying okay, it's going to attach and bind here. Well, it didn't attach and bind there. That was the prediction that they had, but the actual observation was that it ended up going to more places than they thought. The spike protein, the spike protein that was generated, they had put what we call a functional group on the spike protein, and the functional group on the spike protein should have positive and negative attractions to other parts of the cell. So the prediction was that they put something on there and it'll track to something and get stuck. So the spike protein should be immobilized, stationary, but it turned out that wasn't strong enough, and so it went to more places than they had predicted. But that type of stuff is hard to predict. In quantum mechanics, we make predictions, but in order to make proper predictions in quantum mechanics, the math is just too hard. And so we have to make simplifications. And when we make simplifications, it's like the body. The body's complex. Do you know every single reaction? Can you tell me every single reaction that happens in your body? Can you tell me what the purpose of zinc? We need zinc as an essential element, but can you tell me what zinc does in the body and how much we need exactly? And what's the optimum level of zinc and when it becomes poisonous? The same thing with other elements. We need things like selenium. What happens if you don't have any selenium? Do you die? Do you get sick? What happens? Can you tell me? Can you prove to me 100% what happens? No, it's hard. It's hard. And so what we do is we just base it on observations that we've seen. So this type of stuff is difficult. This type of stuff is the debate that happens in science, and it's a very healthy debate. We want these healthy debates to continue. And so some people might want a little bit more evidence in support of certain things than others, And you want those types of people. You want the people that challenge you. Otherwise, and what you want to do is you want to convince those people. And so right now there's a whole bunch of stuff with the climate. Why do they want to ban gas stoves and gas ovens? Because they're worried about climate change. But we should have a healthy debate there. And climate is something that's hard to predict because do you remember the original predictions about the spread of COVID? There's supposed to be millions of deaths according to the models, the mathematical models that they had. The mathematical models didn't turn out to be totally accurate. Well, the same thing. Climate is very difficult to predict because what are the models they're using? And then there are unforeseen reactions that can be happening. And so this should be hashed out. It shouldn't be that, if there are some skeptics, you should work at convincing those. So if there are non-believers for atoms, you should work at convincing them. And so the way that you generate a good consensus is that you have enough evidence in support of whatever you're talking about. But anyway, this is what we have. We have the conservation of matter, and we represent this with what we call balanced chemical equations. So we're going to be talking about chemical equations. So we have one carbon here, one carbon there, and then 2 oxygen. So this is what we call, this would be like burning charcoal. We burn charcoal, eventually it leads to CO2. Over here, this is like putting a 9-volt battery in here, and we don't lose any of them. I asked you which electrode. This was the negative electrode, which generated the hydrogen. This was the positive electrode, which generated the oxygen. And we generated twice as much hydrogen. Why? Because of conservation of matter. Conservation of atoms, conservation of mass. That's why. And so I knew that. That's one of the predictions you can make using the atomic theory. Okay, I'm almost done. But not only do we have conservation of matter and conservation of atoms, we also have conservation of energy. And this is the same thing. This is based on empirical evidence. And so, for example, this would be the combustion of butane. Butane is the gas liquid. Under normal conditions, it's liquid, but it's very volatile. It easily vaporizes. So this, we'd have a little L here. And so when we burn butane, we have to use lots of oxygen in order to generate CO2 to get complete combustion. So for every 2 molecules of butane, we need 13 molecules of oxygen. And then we make 8 molecules of CO2, 10 molecules of water, and we generate a lot of energy. So this would be the combustion of butane and the conservation of mass and energy. So this is showing the conservation of mass or matter or conservation of atoms plus the conservation of energy. We don't always show it like this as balanced, but this would be exothermic. Energy is being generated. If we're endothermic, we put energy on this side because these are what's being consumed in this reaction. And this is a chemical change, a chemical reaction here. And that would be a chemical equation representing it here, exothermic. Now, this is talking about kinetic, and we also have potential energy. And so when we write these reactions like this, we like to keep the kinetic energy the same on both sides. How can I keep the kinetic energy the same on both sides? By keeping the temperature the same. So we start off at 25 degrees C temperature, and we end up at 25 degrees C. That means the kinetic energy didn't change. So here, the kinetic energy is constant, and so we have the change in kinetic energy. The change in kinetic energy, and this might have confused some people, because I saw some people said that the total energy is equal to the change in kinetic energy. No, it's not equal to the change in kinetic energy. The total energy is equal to the kinetic energy, the total kinetic energy that it possesses, not the change in kinetic energy. So the change in kinetic energy here is 0. Because the temperature didn't change. But there is a change in potential energy. And the change in potential energy is, okay, the change in kinetic energy is equal to the kinetic energy final minus the kinetic energy initial. Now, the kinetic energy final is the kinetic energy of the products here. This we call the product. The kinetic energy initial is the kinetic energy initial. Is the kinetic energy final 0? Yeah. No. Because it's at 25 degrees C. The only time the kinetic energy is 0 is when the temperature is equal to what? 0K. 0K. Good. So the kinetic energy is non-zero here. And so we have to be careful about this delta KE. Delta KE just means a change. This still possesses kinetic energy because this is not an absolute 0. Absolute 0 is when all kinetic energy stops, all motion stops. And the same thing over here. This is kinetic energy. Things are in motion. This is liquid. That's a gas. Gases are speeding around.
Is that equal 0?
The change in kinetic energy, delta KE is equal to 0. Now, delta KE is different than what we call absolute kinetic energy. These are the absolute kinetic energy. These are non-zero. We have to be careful. Delta KE can be 0, but there's kinetic energy there because it's at 45 degrees C. And so a number of people wrote delta, the total energy is equal to delta KE plus delta PE. That's wrong. So I marked it wrong. the delta PE here is, there's a change here. And so we're going from higher energy. This is an explosive mixture of butane and oxygen to a lower energy. This is not really explosive here. Okay, let me finish off here with this. Now theories, well, actually, let me continue a little bit here. So endothermic, this will be an example of endothermic. This is photosynthesis here. In photosynthesis, we need magnesium. So people know magnesium and they want to know how it works. Do you know how photosynthesis works? Yeah, light, but how exactly does it work? How exactly does it work is what we want to know. Like, for example, we know that cisplatin works because it killed all the tumor cells, but how did it work? How did it work? And how it works is the mechanism. So how do plants take light and convert it into sugar?
Use it along with carbon.
They use it along with carbon dioxide. So plants take carbon dioxide. This is why we plant more trees. A lot of people are making an effort to get rid of the CO2 by planting more trees, which is great, I think. Because trees. Torrance is a dearth of trees. They need more trees in Torrance. But the city doesn't want to maintain them, so they cut them down. So the CO2 gets converted into wood, basically. Wood is a sugar, but it doesn't taste very good, except for termites. Termites love wood. But wood is made up of the sugar glucose. We can't digest it though. We can digest glucose, no problem, and we can digest starch, no problem. Essentially that. We can't digest wood. But anyway, so people want to know, how it works. And so this is why we want theory, because theory should be able to predict how it works, right? A good theory should be able to. And so a lot of people are looking, the electrons travel, it's like a wire, and the electrons are moving. You get electron transport and all this other stuff. Electrons are moving here and this and that. And anyway, we look at kinetic and potential energy. You talked about this too. Which brings us to this. This holds true. Conservation of energy and conservation of mass. But it turns out that when you look at it in chemical reactions, it's true. But if you look at it in fine detail, and this wasn't noticed until we got to nuclear reactions. When we got to nuclear reactions, then there's this case where the mass initial didn't add up to the mass final. That is, in a nuclear explosion, mass is not conserved. If you started off with 1 gram, you ended up with less than 1 gram. What happened to the mass? How did that mass disappear? Well, in nuclear reaction, what happens is some of the mass gets converted into energy. And so this meant a modification to our law. The modification is, for nuclear reactions, it's conservation of mass and energy. And mass and energy are related by this equation by Einstein here. This very famous E equals mc squared, where some of the mass can be converted into energy. And they're talking about some of the energy can be converted into mass. So like in vacuums, in a pure vacuum, there's no matter in there. But have you heard of they're talking about these they're talking about these weird things where in the vacuum, in a moment, they have these quantum fields or quantum, and all of a sudden some mass appears and the mass disappears. Have you ever heard of something like that? All right, don't worry about it then. You might have heard something about that. But a vacuum,
How does speed of light attributed to this equation?
How is speed of light attributed to this equation? C squared. There are two ways one can think about it. The energy is kilograms for mass, and the speed of light is meters per second. So this is kilogram meter squared per second squared. The kilogram meter squared per second squared is called a joule. And so that's a joule. So we need it for the unit. So it just turns out that mass times the speed of light squared gives you energy. energy units. That's one way we attribute it. That's attributed to what we call dimensional analysis, which we'll talk about later. But why? Science doesn't really describe a lot of why. Science just describes, it just tries to describe nature. Why is the sky blue? Well, it's blue because of the way light is scattered. But why is it blue? It's just blue. It doesn't really, science just describes nature. What do we have? We have 5 minutes left? Yeah? Okay. Then try this in 5 minutes because we know, getting to the greater question, we know how it's blue, but why is green green, Or there's certain things. Green is green because that's the way it's perceived, And so there's different, science describes natures, and that's what scientists do. But try to do this. We have 5 minutes. Let's see how fast your recall is.
Are you doing note cards?
Oh yeah. Let me pass out note cards for this one.
Oh.